So this chapter is about systems of linear equations. So what we're doing in a system of linear equations, and you can see this on a lot of the videos that we have too, like this is not the only notes that you have on this stuff. But in the videos, I really make a big point of trying to discuss how to solve these by graphing and solve them by substitution and solve them by elimination. And you can kind of see like how they all interact and stuff. But basically what's happening here is whenever we solve a system, we're finding the point of intersection of two lines. So what you learned in Algebra 1 is you can solve these by substitution or elimination or by graphing, and then that's kind of what we're reviewing today. So this problem, I would probably try to solve it by elimination. So what I would likely do is I'd pick a variable to try and get rid of. So in this case, I might want to pick, well, it doesn't really matter because this isn't a necessarily easy one to do, but let's say I want to get rid of y. So if I want to get rid of y, I'm going to multiply this top equation by 5 or negative 5. I'll choose negative 5. And then I'll multiply the bottom one by 3. So I have to multiply all of the terms in each of these equations by those numbers. And I'll show you why that works in a second. So we have negative 30x minus 15y equals negative 30. And then the bottom one becomes 24x plus 15y equals 36. So ultimately our goal is, after we multiply these things, we want one of our variables to have the exact same coefficient, but one of them is positive and one of them is negative. That way, when you add the equations together, everything cancels off for that variable, and then you can solve for the variable that's left over. So if I add these two equations together, this is called the elimination method or the addition method. So when I add these two equations together, I get negative 6x. The y's go away, and then this becomes 6. Then I can divide by 6 and get x equals negative 1. Remember, when we're doing systems of equations, we're finding a point. So we're trying to find some kind of coordinate value. So that means in order to find y, I have to take this negative 1 and substitute it back into the original equations. You could pick these new equations, but if you pick the new ones, the numbers are usually bigger. So it's probably better most of the time to choose the original equations. So I'm going to sub negative 1 back in for x in this original equation. So 6 times negative 1 plus 3y equals 6. And then I will solve for y. So 3y equals 12, y equals 4. So since I'm solving for a point, I want to write my answer as a point if it's just a system of two equations. In a word problem, that's different, and we'll do word problems a little bit later in the unit where you have to actually answer things in context. But in problems like this, you want to answer as a point. So the answer to this one is negative 1, 4. I'll do this one, and then if you have any questions, let me know. Problem 6. This problem is very similar, except there are fractions here. Most of us don't like fractions. So the first thing we may want to do is multiply this equation by 2 and this equation by 4, just so then we don't have to think about the fractions anymore. So if I multiply the first equation by 2, that effectively gets rid of the 2 in the denominator. So I have 3x minus y, and then this 5 has to get multiplied by 2 because I multiplied 2 to both sides of the equation. Same thing's going on in the bottom. 4x minus y is going to now end up kind of being all by itself because the 4's end up canceling. And then 4 times 4 gives me 16. So now I have this equation. I can solve this in two different ways. So I'm going to show you both ways to do it. It's actually pretty easy to solve both of them. One way is by substitution. So by substitution, I'm going to get a variable all by itself and then substitute it into the other equation. So let's say I manipulate this first equation to get y all by itself. So I add y over to this side, and I subtract 10 over to this side. So y equals 3x minus 10. So I just do a little bit of manipulation. What I can then do is I can take this y equals 3x minus 10, and I can substitute it into the y in the other equation. So I have 4x minus 3x minus 10 equals 16. I can then distribute the negative 1, so 4x minus 3x plus 10 equals 16. I get x equals 6 after I simplify. So this becomes x. I subtract the 10 over. And then I can take this 6 and I can sub it in to any one of the equations up here and find y. This one is actually probably the easiest one to sub it into because I already have y all by itself. So if I take 6 and plug it in, I get 3 times 6 minus 10 is my y value in this case. And that gives me 8. So the answer would be 6, 8. I can also do this by elimination. So if I look at the two equations that I have, I can multiply one of them by negative 1. And this is actually an easier way to solve this question at the moment. So if I multiply this one by negative 1, I have negative 3x plus y equals negative 10. And I have 4x minus y equals 16. Well, notice that the y's are going to go away. The x's, 4 minus 3 is just 1x, and then 16 minus 10, or negative 10 plus 16 gives me 6. And then when I substitute 6 in, 24 minus y equals 16, subtract that over, negative y equals negative 8, so y equals 8. So I end up getting the same answer either way. So both ways are good ways of doing the problem. So number 7, now notice a lot of these problems have letters that aren't x and y. So when I write the answer, I'm still going to write it as a point, and it's going to be alphabetically. So in this case, C and K, C would come first and K would come second. So you kind of go in the order of the alphabet. So this problem, I mean, you could leave it like this, but most of the time I don't know why I chose to write an 8 like that. That was kind of strange. Most of the time, we probably want to get it into standard form just for our mental purposes. So I get it to look like this. And then probably the best way to go about this is just to multiply this top one by negative 2. Now, how do I come up with the way to multiply these things? Well, my objective is to try and, as easy as possible, get one of the letters to have a positive and a negative of the exact same number. So if I look at 8 and 10, I could multiply the top one by something and the bottom one by something. But if we look at 3 and 6, those are multiples of each other. So that's probably an easier way to do it. So negative 16c minus 6k equals positive 10. So then I add things. I end up with negative 6c. The k's go away. And this is negative 3. So divide both sides by negative 6. Negative 3 divided by negative 6 is 1/2. So c equals 1/2. And then I can take that and substitute it back into either equation. I'll choose this one because the numbers are smaller. So 8 times 1/2 plus 3k equals negative 5. 8 times 1/2 is 4. Subtract 4 and divide by 3, and I get k equals negative 3. So my final answer in this problem is 1/2 negative 3. Once again, what that actually represents is where those lines intersect. So what I'm going to do really quick is we're going to pretend like c is x and k is y. So what I can do is I can take these two equations, I'm just pretending that x is c and y is k, just so then I do it alphabetically. So I take these equations and I plug them in, and I end up getting an intersection point. This intersection point is what we're solving for. So when I solve a system of equations, what I'm really doing is I'm finding an intersection point. So if I go back to here, this represents where the lines intersect. Okay. Number 8 is a slightly harder version of number 6 because we have a bunch of fractions and most of us don't like to add or subtract fractions. So in order to get rid of the fractions, what I would do is I would multiply both of these equations by whatever the common denominator of this equation is. So the top one has a common denominator of 20 because 5 and 4, the least common multiple of 5 and 4 is 20. For this one, the least common multiple of 2 and 4 is 4. So if I multiply these equations by these, then I don't have to worry about the fractions anymore. And I can kind of not have to worry about that nearly as much. There's probably another way of doing it, but in the interest of time, I'm not going to worry about it too much. So now what I'm going to do is I'm just going to multiply everything across. So 20 times 2j over 5 becomes 40 over 5 times j. Well, 40 over 5 is 8, right? And then 20 times 3 is 60. 60 over 4 is 15. So I have 8j minus 15x equals negative 40. Then for number 8, 4 divided by 2 is 2j. 4 divided by 4 is 1s, and 7 times 4 is 28. So I can just kind of multiply those things, and it ends up working out relatively nicely there. Okay, so now I can kind of just pick my thing that I want to do. So I can multiply the bottom one by 15 to get rid of the s's, or I can multiply the bottom one by negative 4 to get rid of the j's. Negative 4 means the numbers are going to be a lot smaller for my work, so I'm going to multiply it by negative 4. But you could do it another way, and it's not like it's wrong. Okay, so now I have negative 8j minus 4s, so that's just multiplying. And then that equals 28 times 4, so that would be 112, I'm pretty sure. Negative 112. Now I just add, so I have negative 19s equals negative 152. And negative 152 divided by 19 gives me 8. So s is 8. And then I can solve for j. I probably want to plug it into this because it's just a blank s, and that's pretty easy. So 2j plus 8 equals, what was that again? 28. Subtract 8 and divide by 2, you get j equals 10. So then you want to put them in alphabetical order, which is j first and s second. So 10, 8 is my answer for this problem. If you have questions, just kind of interrupt me in the chat about anything. I'm going to show you 2 ways to do number 12. I think the first way is probably easier. If you notice, 3 is a common multiple of all of these things. Can you use substitution to solve number 8? Yes. So once you get here, you can use substitution with s. Or in a very advanced case, you can use s over 4 equals 7 minus j over 2. and substitute this in here if you wanted for s over 4, and then just multiply this by 3. But I wouldn't recommend that. There's a lot of room for mistakes. But yes, you can use substitution. In this one, I think probably the easiest way to do number 12 is to see that all of these are multiples of 3. And divide all of these by 3. So you can have j minus k equals -4. And that ends up working out really easy because like most of us don't like fractions, but this isn't a hard fraction to deal with. The k's are now just going to cancel right away. And so I have 1/2 plus 1, that's 3/2. J equals 5. And then I cross multiply and I get j equals 10/3. So, or I multiply by the reciprocal, I'm sorry. So times 2 and divide by 3. And then I get j. And then I can just take this and substitute it in and solve for k. So if I put it into the bottom one, I get 10/3 minus k equals -4. So k equals 10/3 plus 4, and 4 is 12/3. So k equals 22/3. So my answer would be 10/3, 22/3. Okay. The other way of doing this problem is to multiply the top one by 2 to get rid of the fraction. Oops, that should be 2k. And then I can probably still divide this by 3, but I might want to divide it by -3. So -j plus k equals +4. And then you get 3k equals 22. And then you would solve in the same way. You'd get k equals 22/3, plug that into one of the equations, and you'd get j equals 10/3. So 10 and 13 are kind of special cases. So if we subtract the y over in this one, I mean, you can do this by substitution too, so I'll do it both ways. But if you subtract the y over in the bottom one, you have 4x minus 2y equals 5, and 2x minus y equals -1. So what I would do, probably, is multiply the bottom one by -2. So I have 4x minus 2y equals 5, and -4x plus 2y equals 2. If I add these together, I get 0, 0. Whoa, they're all 0 over here. So everything cancels out. Well, if everything cancels out and you end up with something equals something that's not it, this doesn't make any sense. If it makes no sense, no solution. The vocabulary word we use for that is inconsistent. And if I just graph these two things, what I'm going to find, it was, I think, 4x minus 2y equals 5, and it was 2x minus y equals -1. I think those were the two. What we end up with is we end up with lines that never intersect, right? So these are called parallel lines. So we have two lines that never intersect, they're parallel. And if we end up with an equation when we set up the system and we solve it, where we end up with a number equals some other number, like if all the x's and y's go away and we end up with some number equaling another number, that doesn't make any sense. There's no solution, we have parallel lines. We can also solve this by substitution if you wanted. So you could say y equals 2x plus 1 by adding the 1 over. And then taking this and substituting it in here. So 4x minus 2 times 2x plus 1 equals 5. If I distribute, I have 4x minus 2 equals 5. So those cancel. I get negative 2 equals 5. That makes no sense. No solution. So it doesn't matter if you solve it by substitution or elimination. You should get the same result. You should get the same point, or you should get the fact that there's no solution. Or in number 13's case, what I'm going to do is I'm going to multiply this one by the common denominator, which is 6. And I'll get negative 3x plus 2y equals 24. And let's combine that with the bottom system equation. And I get 0, 0, and 0. So if I get 0 equals 0, that works all the time. Like 0 always equals 0. So if I get rid of all of the variables, and if it works all the time, infinitely many solutions. The vocabulary word we use in that class, or in this class for that, is dependent. So the solutions are, or the system is dependent. Okay. So what that looks like graphically is, what did I have? 3x minus 2y equals negative 24. And negative 1/2 x plus 1/3 y equals 4. So notice what happens. They are on the same line. So they're actually exactly the same line. It's very important that we understand that this does not mean all real numbers. So this is kind of different from last chapter. All real numbers means that every single number works. Notice that there are lots of things that don't work. Like, for example, the point negative 2, 3. Does negative 2, 3 make this work? No, negative 2, 3 is not on the line. So there are lots of things that don't make it work. There are actually more things that don't make it work than do make it work. So we can't say all real numbers. But there are an infinite amount of solutions. Okay, like any point on this line makes it work. So for example, negative 8, 0 makes it work. 0, 12 makes it work. There are lots and lots of things that make it work. Negative 4, 6, any of these decimals in between, they all make it work. We just can't say that everything makes it work because everything doesn't. Okay, any questions on the special cases? All right, next. All of that was stuff that we did in Algebra 1. So now we're going to start talking about things that are new to Algebra 2. First is variables in the denominator. So these are not lines, but the reason we do them in this chapter is we can kind of treat them like lines. So I'm going to do both of these problems 2 different ways really fast to try and help us understand the way to go about it. The first way is to treat them like lines. And the way you can treat them like lines is make 1 over x equal to a and 1 over y equal to b. So what would that look like? Well, 8 over x is really the same thing as 8 times 1 over x. And 3 over y is really the same thing as 3 times 1 over y. So if I have this, what I can do is I can replace 1 over x and 1 over y with a over b, and then I basically have something that I've seen all the time. So 8a plus 3b equals negative 6. So I can make a substitution that makes my life easier. And we've solved tons of equations like this. So what I can do then is I can multiply the bottom one by negative 2, and then I have 8a plus 3b equals negative 6, and negative 8a plus 10b equals negative 46. And I can continue to solve. I get 13b equals negative 52. And b equals negative 4. Then I can plug that back in to one of these equations, probably this one because the numbers are smaller. So 4a minus 5 times negative 4, so negative 5 times negative 4 becomes 20. Subtract 20 and divide by 4, a equals 3/4. That wasn't that hard. You know, we've solved tons of problems like this. The only thing we have to remember is that the problem was in x's and y's, and we have answers in a's and b's. So if we make this substitution, we then have to remember that we have to find x and y. So a is 3 over 4. That's equal to 1 over x. B is equal to negative 4. That's equal to 1 over y. So I have to take these things and solve them. And so I end up with, I can cross multiply and do all that stuff. X equals 4/3, and B, I'm sorry, I don't care about B. I already got B. Y equals negative 1/4. And that I can do with like solving, or I can just realize that 1 over x is the reciprocal of a. So x is the reciprocal of a, and y is the reciprocal of b. So I can just like flip the top and bottoms if I don't want to do the solving. Like that's kind of what's happening. Okay, I'll do one more example, exactly the same. And if you have questions on it, let me know. So if a is 1 over x and b is 1 over y, I can rewrite this to be 4a minus 3b equals negative 19 over 2, and negative 7a minus 1b, or minus b, equals 1. Then you have a couple choices. You can decide whether you want to get rid of the fraction or not. Since something divided by 2 is not really that hard, I'm probably not going to get rid of the fraction. So I'm going to multiply this equation by negative 3. So the top one is 4a minus 3b equals negative 19 over 2. And the bottom one is 21a plus 3b equals negative 3. Then I add these, I get 25a, the b's cancel, and negative 19 over 2 minus 6 over 2, because 3 is really the same thing as negative 6 over 2. So this becomes negative 25 over 2. If I divide by 25, I get a equals negative 1/2. Then I can take that, sub it back into either equation. If you sub it in here, it ends up being a nice number. So 4 times negative 1/2 is negative 2. I add 2 to both sides. So 2 is really 4/2, so I have negative 15 over 2. Then if I divide by 3, or negative 3, I get b equals positive 15 over 6, which can reduce to 5 over 2. So A is -1/2, B is 5/2. So remember I have to solve for x and y. 1 over x equals a, which kind of means that x is 1 over a, so I can flip the top and bottom. 1 over y equals b, which means that y equals 1 over b, so I can flip the top and bottom. So if I want x, I take -1/2 and I flip it, so I get -2. Y, I can flip this and it becomes 2/5. So my answer is -2, 2/5. All right, any questions on that? Okay.
When you
Yeah,
write
go
the
ahead.
A is one, like the A, it will always, so no matter what problem you do, if we write the variables and make it A and B, they can equal it that way, basically. So it doesn't matter what problem we have, we can use that to find and solve the answer.
Like in problems like these where the variables are in the denominator?
Yeah.
Yeah, that's something that you can use in any problem like this.
Okay.
In the interest of time, if you want to use another method for this, you're going to have to watch the video that I had from that is going to be on the calendar for solving those types of problems. So if you want to use another method to solve them that doesn't involve a substitution, you'll have to watch that video just because we're not going to have enough time to go over it today. Okay, then the last thing that we're going to go over today are 3x3 systems. So those are systems that have 3 variables. Basically, what we're going to do is our answer is going to be a point in 3 dimensions. And if you want to know what is actually happening, I'll really briefly explain it, but I have something that'll be on the calendar after I finish the calendar for this unit that talks about like and shows you a picture of what this looks like. But you basically have 3 planes. So if you remember from geometry, you have points and lines, and then planes are like 3-dimensional flat surfaces. These are 3 planes, and we're finding the point where those 3 planes intersects. Okay, so that's kind of what's happening here. So let's take a look at this one. Well, in this case, I kind of started us off with a really easy one because z is in an equation all by itself. So z equals -4. So that makes us happy because we don't really have a whole lot of stuff to do. Now what I can do is I can take this z equals 4. I can plug it in for z here. And now I have equations that already have the z's in it. So, or already have gotten rid of the z's. And now I just have a thing that I'm already used to doing. So x minus 4y minus 12 equals -27. That's what happens when I put the -4 in here. And 2x plus 2y plus 12 equals 22. So if I get these to be in standard form, x minus 4y equals -15, and 2x plus 2y equals 10. So now I can just pick one to multiply by 2, because I can either get rid of the x's or get rid of the y's. So x minus 4y equals -15, 4x plus 4y equals 20, 5x equals 5, x equals 1. I take x equals 1 and plug it into something. I can do that here. And I get 2 plus 2y equals 10, 8, and then 8 divided by 2 is 4. So y is 4. So notice I now have an x, a y, and a z, and I can write that as a point, 1, 4, negative 4, and I have my answer. So this problem is way easier than most of the ones you're going to get that are 3x3 systems, but it kind of shows you the goal. The goal is to get the thing to look like a 2x2 system because we know how to solve those. So if we can get one of the things to kind of go away and make it look like a 2x2 system, then we know how to solve that, and then it's not that big of a deal. Questions before I move on to the last problem we're doing today? Okay, so we're going to do problem 6 on worksheet 2 also. So this was problem 1 on worksheet 2. Problem 6 on worksheet 2 is, well, it's a little bit more complicated. But if you notice, all of the y's are like just singular y's. So here's our goal. Our goal is to get 2 different equations with the same variable eliminated. That's our goal. And the good news is I can get that pretty easily in this one, because if I group numbers 1 and 2 and I add them together, what's going to happen? 2x plus 4x is 6x. Y plus negative y goes away. 2z minus z gives me z. And then I have negative 11. If I group the second and the third equations, I'll do a different color so then it's easier to see. If I do the second 2 equations, 4x minus 3x gives me x. Negative y plus y, they go away. And then this becomes 4z equals positive 2. So notice what happens. If I group the first and the second, and I group the second and the third, if I just add the first and the second together, and I add the second and the third together, now what do I have? I have something that I know how to do. So that's our goal. Our goal is to get it into something that we know how to do and then go from there. So since I know how to do this one, now what I'm going to do is I'm going to multiply this by negative 4. No, poor choice. Multiply that one by negative 6. That would get rid of the x's. So I have 6x plus z equals negative 11. And negative 6x minus 24z equals negative 12. Negative 23z equals negative 23. So z equals 1. And then once I get one of them, I can then probably get everything else. So plug z in here. X plus 4 equals 2. Just plug it into the green one. Subtract, I get x equals negative 2. Now I can take the thing I know about x and the thing I know about z and plug them into one of these equations. And then I can find y. So 2 times negative 2 gives me negative 4 plus y, that's the last thing I have to find, minus z, which is 1, equals negative 8. Negative 4 minus 1 is negative 5. Add 5 to both sides, I get negative 3. So my answer, x comma y comma z, is negative 2 comma negative 3 comma 1. So if I start by getting it into something that I know how to do, then I can go from there and I just solve and then kind of move myself up the ladder. So I get z equals 1 first. You don't have to get z first. That's how it worked out in this problem. Then I got x next, and then I put it all into one equation and I got the final answer.